The universe, 100 billion galaxies, each containing 100 billion stars, a 13.8 billion year old story of cosmic evolution, governed by immutable laws of physics. But what if those laws are not laws at all? What if they are code? The idea that we are living in a simulation is no longer confined to science fiction. It has moved from philosophical thought experiments into the realm of theoretical physics. But to ask this question scientifically, we must discard popular notions of glitches in the matrix, a floating cup, a moment of déjà vu. These are artifacts of human perception. If we are to find the glitch, we must look for it not in our psychology, but in the cosmos. We must hunt for an artifact, a limitation, a seam in the very fabric of space-time. We must search for the processor speed limit of the cosmos. The modern scientific inquiry begins with a trilemma, a powerful logical argument. It states that one of three propositions must be true. 1. Civilizations like ours almost always go extinct before reaching the technological capacity to create high-fidelity ancestor simulations. 2. Civilizations that do reach this stage simply have no interest in running such simulations. Or 3. The number of simulated realities is astronomically larger than the one base reality. If proposition 3 is true, then by simple probability, we are almost certainly not the originals. This is a philosophical anchor, but it is not physical proof. To find that, we must understand how a simulation would be built. Any simulated universe, no matter how vast, would be limited by the computational resources of its host. It cannot have true infinity. Its physics must be calculated. To do this efficiently, a simulator would not render the universe as a smooth, continuous whole. That would require infinite data. Instead, they would build it on a discrete lattice. Like the pixels on a screen, this lattice would represent the smallest possible unit of space and time, a fundamental resolution to reality itself. To us, living inside, this grid would be invisibly small, perhaps near the Planck length, 10 to the power of -35 meters. From our perspective, the universe would appear perfectly smooth, perfectly continuous, almost. How do you find the grid? You push the system to its absolute limit. We must look at the fastest, most energetic particles ever observed, ultra-high energy cosmic rays. These are protons and atomic nuclei, remnants of cataclysmic events, accelerated to near the speed of light and fired across intergalactic space. They are the universe's ultimate particle accelerator. For decades, we have believed there is a natural speed limit for them. It is called the GZK cutoff. The GZK limit is not a wall. It is an interaction. As a proton travels with an energy above 50 exelectron volts, it begins to see the faint afterglow of the Big Bang, the cosmic microwave background, as a violent hailstorm. The proton collides with these low-energy photons, producing new particles, and in doing so, it loses energy. It slows down. This interaction is fundamental. It means that no matter how energetic a particle is when it leaves its distant galaxy, by the time it reaches us, it should be below this GZK energy cap. And crucially, the cosmic microwave background is isotropic. It's the same in all directions. Therefore, this energy limit should be the same, no matter where we look in the sky. But what if it isn't? This is where we find a glitch. Physicists, including a team led by Silas Bean, have proposed a test. If the universe is a simulation running on a cubic lattice, that lattice also imposes a maximum energy limit. But unlike the GZK limit, this new limit would not be the same in all directions. A particle traveling diagonally across the simulation's grid would have a different maximum energy than a particle traveling perfectly along one of its axes. The result? The uniform GZK cutoff would be replaced by something else. We would observe an anisotropy in the sky. The maximum energy of cosmic rays arriving from that direction would be different from the maximum energy of those arriving from this direction. The distribution of the most powerful particles in the universe would not be random. It would be imprinted with the grain of the simulation. It would betray the preferred directions of the underlying lattice. This is a specific, falsifiable prediction. We are building the observatories to look for it right now. Of course, there is a powerful counterargument. Based on the known laws of physics, specifically the holographic principle and the Bekenstein bound, which defines the absolute limit of information in a given volume, we can calculate the computational cost of simulating our universe. The answer is staggering. To simulate just the observable universe down to the quantum level, it would require a computer that contains more energy, more information than the entire universe itself. This suggests that our universe cannot be simulated by a computer existing within a universe like ours, unless the physics of the base reality are fundamentally different and vastly more resource-rich than our own. Or perhaps the simulation is not as high fidelity as we assume. Perhaps it's not a perfect quantum simulation. Perhaps the simulation only renders what is observed. This is a chilling echo of the strangest aspect of quantum mechanics itself, the measurement problem, that a particle state is not defined until it is measured. We are left with a profound possibility. We may be on the verge of proving that our reality is an emergent property, or we are on the verge of proving that the most energetic particles in the cosmos behave in a way we have yet to understand. Either way, the hunt for the lattice, the search for the grain in the fabric of reality, has begun.